What if everything you thought you knew about the universe was just the tip of the iceberg? Picture this: the cosmos is stretching, growing, and accelerating faster than we can even measure. And here's the kicker: what we see with our most powerful telescopes is only a tiny fraction of what's really out there. Sounds like science fiction, right? But it's not. This is the reality of our expanding universe, and it's more mind-blowing than you can imagine. Welcome to a journey through the cosmos, where we'll uncover 25 astounding facts about the expanding universe. From the mysterious force of dark energy to the mind-bending idea that the universe has no center, we're diving deep into the secrets of space. You'll learn how the Big Bang wasn't an explosion, why galaxies are racing away from each other, and what the universe's ultimate fate might be. So, buckle up and get ready to have your perspective on the cosmos completely transformed. By the end of this video, you'll see the universe in a whole new light, and trust me, it's going to blow your mind. Let's dive in. Now, let's zoom in on our first astounding fact. The universe is expanding faster than we ever imagined. Back in the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. By observing distant galaxies, he noticed something peculiar: they were all moving away from us. This phenomenon, known as redshift, revealed that the universe wasn't static but stretching out in all directions. But here's where it gets even more fascinating. Decades later, scientists studying supernova found that this expansion isn't just happening, it's speeding up. What's causing this acceleration? Enter dark energy, a mysterious force that makes up about 68% of the universe. Unlike gravity, which pulls things together, dark energy pushes space apart, acting like an invisible engine driving the cosmos to expand faster and faster. This discovery completely reshaped our understanding of the universe's fate. Instead of slowing down or collapsing back in on itself, the cosmos is on a trajectory to keep growing, possibly forever. So, what does this mean for the future? If dark energy continues to dominate, galaxies will drift farther apart, and the universe will become colder, darker, and more isolated. It's a humbling thought, but it also reminds us just how dynamic and mysterious the cosmos truly is. And this is just the beginning. There's so much more to uncover as we continue to explore the expanding universe. Now, let's tackle a common misconception about the birth of our universe. When we hear the term Big Bang, it's easy to picture a massive explosion like a cosmic firework lighting up the darkness. But here's the twist: the Big Bang wasn't an explosion at all. Instead, it was the rapid expansion of space itself. Imagine blowing up a balloon. As you inflate it, every point on the balloon's surface moves away from every other point. There's no center, no single point where the expansion begins. It's happening everywhere at once. That's exactly how the universe expanded during the Big Bang. This idea can be a little mind-bending, but let's break it down. The Big Bang didn't happen in a specific location in space. It happened everywhere. Space itself stretched, carrying matter and energy along with it. Think of it like baking raisin bread. As the dough rises, the raisins move farther apart, not because they're traveling through the dough, but because the dough itself is expanding. In the same way, galaxies aren't flying away from a central point, they're being carried apart by the stretching of space. This concept also helps explain why the universe has no center. If you were to rewind time, you wouldn't find a single point where everything began. Instead, you'd see all of space shrinking uniformly, like deflating that balloon. This uniform expansion is why we say the Big Bang happened everywhere at once. It's a subtle but crucial distinction that reshapes how we think about the origins of the cosmos. So, the next time someone mentions the Big Bang, remember, it wasn't an explosion in space, it was the expansion of space itself. And just like that balloon, the universe is still stretching, carrying galaxies farther apart as we speak. It's a fascinating reminder of how the cosmos works on scales that are both unimaginably vast and beautifully simple. Now, let's zoom out even further and consider just how much of the universe we can actually see. The observable universe is the portion of the cosmos that we can detect from Earth, limited by the distance light has had time to travel since the Big Bang. But here's the mind-blowing part. This observable universe is just a tiny fraction of the entire cosmos. In fact, it's like looking at a single grain of sand on an endless beach. The reason for this limitation lies in something called the cosmic horizon. Think of it as the edge of our cosmic bubble. Because the universe is about 13.8 billion years old, light from objects farther away than that hasn't had enough time to reach us yet. It's like standing in a dark forest with a flashlight. You can only see as far as the light can travel. Beyond that, everything is shrouded in darkness. But here's where it gets even more fascinating. The universe is expanding, and as it does, distant galaxies are moving away from us faster than the speed of light. This means that light from those galaxies will never reach us, effectively placing them beyond our cosmic horizon. It's a bit like trying to catch a train that's already left the station. It's simply out of reach. So, while the observable universe is staggeringly vast, filled with billions of galaxies, stars, and planets, it's just a small slice of the entire cosmos. The rest remains hidden, a mystery waiting to be unraveled. And who knows, beyond that cosmic horizon, there could be entire realms of space and time that we can't even begin to imagine. This idea reminds us that, even with all our advanced technology and knowledge, there's still so much about the universe that lies beyond our grasp. It's a humbling thought, but also an exciting one, because it means the cosmos still holds countless secrets waiting to be discovered. Now, let's turn our attention to one of the most baffling and intriguing forces in the cosmos: dark energy. Imagine the universe as a vast, ever-growing tapestry, and dark energy is the invisible hand pulling it apart at an ever-increasing rate. This mysterious force makes up about 68% of the universe, yet we still know very little about what it actually is. Dark energy was first discovered in the late 1990s when astronomers observed that distant supernovae were fainter than expected. This suggested that the universe wasn't just expanding, it was expanding faster and faster over time. This discovery turned our understanding of the cosmos on its head. Instead of gravity slowing down the expansion, as scientists had assumed, something was pushing it to accelerate. That something is dark energy, but what exactly is dark energy? That's the million-dollar question. Some theories suggest it's a property of space itself, a kind of energy woven into the fabric of the universe. Others propose it could be a new kind of field or force, entirely different from anything we've encountered before. What we do know is that dark energy is the driving force behind the universe's accelerated expansion, stretching space itself and pushing galaxies farther apart. Here's where it gets even more mind-bending. As the universe expands, dark energy becomes more dominant. Over time, it could grow so powerful that it overwhelms all other forces, potentially leading to a future where galaxies, stars, and even atoms are torn apart. This idea, known as the Big Rip, is just one of the many possibilities that dark energy presents. Yet, despite its overwhelming presence, dark energy remains one of the greatest mysteries in cosmology. We can't see it, touch it, or directly measure it. All we know is that it's there, shaping the fate of the universe in ways we're only beginning to understand. It's a reminder that even as we uncover more about the cosmos, there's still so much we don't know, and that's what makes the journey of discovery so thrilling. As we continue to explore the universe, dark energy stands as a testament to the endless mysteries that await us. It challenges our understanding of physics, pushes the boundaries of our knowledge, and keeps us asking the big questions about the nature of reality itself. Now, shifting our gaze to the stars, let's explore a discovery that fundamentally changed our understanding of the cosmos: the fact that galaxies are moving away from each other. This revelation came thanks to the pioneering work of astronomer Edwin Hubble in the early 20th century. Hubble observed something extraordinary when he studied the light coming from distant galaxies. He noticed that the light was shifted toward the red end of the spectrum, a phenomenon now known as redshift. To understand redshift, think of it like this. Imagine you're standing on a train platform and a train is moving away from you while blowing its horn. As the train gets farther away, the sound of the horn becomes lower in pitch. This is called the Doppler effect, and something similar happens with light. When a galaxy moves away from us, its light stretches out, shifting toward the red end of the spectrum. The greater the redshift, the faster the galaxy is moving away. Hubble's observations showed that almost every galaxy he studied was redshifted, meaning they were all receding from us. But here's the kicker. It's not just that galaxies are moving away from us, they're moving away from each other too. This was the first solid evidence that the universe itself is expanding. To visualize this, picture a loaf of raisin bread baking in the oven. As the dough rises, the raisins move farther apart from one another. It's not that the raisins are moving through the dough, rather, the dough itself is expanding, carrying the raisins along with it. In the same way, galaxies aren't just drifting through space. Space itself is stretching, carrying galaxies with it as it expands. This discovery was groundbreaking because it provided the first observational evidence for the Big Bang theory, showing that the universe had a beginning and has been expanding ever since. It also laid the foundation for our modern understanding of cosmology, including the role of dark energy in accelerating that expansion. So, the next time you look up at the night sky, remember that the galaxies you see aren't just sitting still, they're part of a vast, ever-expanding cosmic dance, moving farther apart as the universe stretches into the unknown. And it all started with Edwin Hubble's keen observations and a simple but profound shift in the color of light. Now, let's take a step further into the cosmic mystery and explore a concept that might bend your mind a little. The universe has no center. That's right, despite what you might imagine, the Big Bang wasn't an explosion that happened at a single point in space. Instead, it was the rapid expansion of space itself, everywhere at once. To wrap your head around this, let's revisit the balloon analogy we touched on earlier. Imagine the surface of a balloon covered with tiny dots. As you inflate the balloon, every dot moves away from every other dot. No single dot is the center of this expansion, it's the entire surface of the balloon that's stretching. In the same way, the universe isn't expanding from a central point. Space itself is stretching uniformly in all directions. This means that no matter where you are in the universe, you'd observe the same thing. Galaxies moving away from you in every direction. It's not that you're at the center, it's that every point in the universe sees itself as the center of expansion. This idea can feel counterintuitive because we're used to thinking of explosions as starting from a single location. But the Big Bang wasn't an explosion in space, it was the expansion of space itself. So why does this matter? Well, it fundamentally changes how we understand the cosmos. If the universe had a center, it would imply a special location, a kind of cosmic home base. But the fact that it doesn't tells us something profound. The universe is uniform and isotropic, meaning it looks the same in all directions, no matter where you are. This uniformity is one of the key pieces of evidence supporting the Big Bang theory and our modern understanding of cosmology. As we continue to unravel the mysteries of the cosmos, remember this: the universe isn't expanding into anything and it doesn't have a center. It's simply stretching, carrying galaxies along with it in a grand, ever-growing tapestry of space and time. And with that, we're ready to dive into the next astonishing fact about our expanding universe. Now, let's turn our attention to one of the most remarkable discoveries in modern cosmology: the cosmic microwave background, or CMB. Think of the CMB as the universe's baby picture, a faint glow that fills the entire cosmos and gives us a glimpse of what the universe looked like just 380,000 years after the Big Bang. This ancient light is the afterglow of the Big Bang itself. and it's one of the strongest pieces of evidence we have for the theory of the universe's explosive beginning. The story of the CMB's discovery is as fascinating as the phenomenon itself. Back in the 1960s, two scientists, Arno Penzias and Robert Wilson, were working with a large radio antenna in New Jersey. They kept picking up a strange, persistent noise, a faint hiss that seemed to come from every direction in the sky. At first, they thought it might be interference from nearby radio signals or even pigeon droppings on their equipment. But after ruling out every possible explanation, they realized they had stumbled upon something extraordinary: the CMB, the oldest light in the universe. So, what exactly is the CMB? Imagine the universe in its infancy, a hot, dense soup of particles and energy. At that time, it was so hot that light couldn't travel freely. It was constantly scattered by free electrons. But as the universe expanded and cooled, electrons combined with protons to form neutral atoms, allowing light to travel unimpeded for the first time. This light, released nearly 13.8 billion years ago, has been traveling through space ever since, stretched and cooled by the expansion of the universe into the faint microwave radiation we detect today. The CMB is like a time capsule, preserving a snapshot of the universe at a critical moment in its history. By studying its tiny fluctuations, regions that are slightly hotter or colder than average scientists can learn about the early universe's structure and composition. These fluctuations are the seeds of the large-scale structures we see today, like galaxies and galaxy clusters. In a way, the CMB is the blueprint for the cosmos as we know it. What makes the CMB so astonishing is how uniform it is. No matter where you look in the sky, the temperature of the CMB is almost exactly the same, varying by just a few millionths of a degree. This uniformity supports the idea that the universe is isotropic, the same in all directions, and provides crucial evidence for the Big Bang theory. It's a humbling reminder that the universe we see today, with its vast galaxies and intricate structures, began as a hot, dense, and incredibly uniform sea of energy. As we continue to explore the mysteries of the cosmos, the CMB remains a cornerstone of our understanding. It's a testament to the power of science to uncover the secrets of the universe, even when those secrets are hidden in the faintest whispers of ancient light. And with that, we're ready to move on to the next astonishing fact about our ever-expanding universe. Now, let's take a step back in time, way back, to uncover one of the most fundamental questions in cosmology: how old is the universe? The answer, as it turns out, is remarkably precise. The universe is 13.8 billion years old. But how did scientists arrive at this number, and why is it so important? Let's break it down. To determine the age of the universe, scientists rely on a combination of observations and calculations, with the cosmic microwave background playing a starring role. Remember the CMB we just discussed? That ancient light isn't just a snapshot of the early universe, it's also a cosmic clock. By measuring the temperature and fluctuations in the CMB, scientists can trace the universe's expansion backward to its very beginning. This method, combined with data from other sources like the Hubble constant, which measures how fast the universe is expanding, gives us a clear picture of the universe's age. But here's where it gets even more fascinating. The precision of this measurement is astounding. Think about it. We're talking about an age calculated to within just a few tens of millions of years. That's like measuring the length of a football field down to the width of a single blade of grass. This level of accuracy is a testament to the incredible advancements in technology and the meticulous work of scientists over decades. So, why does this number matter? Knowing the age of the universe isn't just a fun fact, it's a cornerstone of our understanding of cosmology. It helps us piece together the timeline of cosmic events, from the formation of the first atoms to the birth of stars and galaxies. It also provides a framework for testing other theories about the universe, like the nature of dark energy and the ultimate fate of the cosmos. In short, it's a key piece of the puzzle that helps us make sense of everything we see when we look up at the night sky. As we marvel at this precise measurement, it's worth reflecting on how far we've come in our quest to understand the universe. From ancient stargazers to modern cosmologists, humanity's curiosity has driven us to uncover the secrets of time itself. And with that, we're ready to explore the next astonishing fact about our ever-expanding universe. Now, shifting our gaze to the vastness of space, let's explore a fact that might seem counterintuitive at first. The universe is mostly empty. Yes, despite the countless stars, galaxies, and cosmic wonders we see, the cosmos is overwhelmingly a void. To put it into perspective, imagine the entire universe as a giant, almost empty room. The stars and galaxies, they're like tiny specks of dust floating in that room, separated by unimaginable distances. Take our own Milky Way galaxy, for example. It's home to hundreds of billions of stars, yet the average distance between them is about 4 light years. That's roughly 24 trillion miles. To visualize this, think of 2 grains of sand placed over 6 miles apart. That's how sparse stars are, even within a galaxy. And when we zoom out to the scale of the entire universe, the emptiness becomes even more staggering. The nearest galaxy to the Milky Way, Andromeda, is a whopping 2.5 million light-years away. That's a distance so vast it's almost impossible to comprehend. But why is the universe so empty? It all goes back to the Big Bang and the way space itself has been expanding ever since. As the universe grows, matter spreads out, creating these vast cosmic voids. And while we might think of space as being filled with stars and planets, the reality is that these objects are just tiny islands in an endless ocean of nothingness. This emptiness has profound implications for our understanding of the universe. For one, it explains why space travel between stars is such a monumental challenge. Even if we could travel at the speed of light, it would still take years to reach the nearest star. It also highlights just how unique and precious our own little corner of the cosmos is. Earth, with its abundance of life, is a rare oasis in an otherwise desolate expanse. So, the next time you look up at the night sky and marvel at the countless stars, remember this: what you're seeing is just a tiny fraction of the universe. The rest, it's an unimaginably vast, empty canvas waiting to be explored. And with that, we're ready to dive into the next astonishing fact about our ever-expanding universe. Now, let's turn our attention to one of the most profound questions in cosmology. What lies ahead for the universe? The fate of the cosmos is a topic that has fascinated scientists and dreamers alike, and there are several compelling theories about how it all might end. One of the leading ideas is the Big Freeze, also known as the heat death of the universe. In this scenario, the universe continues to expand at an accelerating rate, driven by dark energy. Over trillions of years, galaxies will drift farther apart, stars will burn out, and the universe will grow colder and darker until it reaches a state of near-total stillness. It's a chilling thought, but one that aligns with our current understanding of dark energy's relentless push. On the other hand, there's the Big Crunch, a dramatic reversal of the Big Freeze. In this theory, the expansion of the universe could eventually slow down and reverse, causing everything to collapse back into a single point. Imagine the universe contracting like a deflating balloon, with galaxies, stars, and even atoms being crushed together. This scenario hinges on the idea that dark energy might weaken over time, allowing gravity to take over and pull everything back. It's a cosmic do-over, but one that would mark the end of everything as we know it. Then there's the Big Rip, perhaps the most dramatic of all. In this theory, dark energy doesn't just keep the universe expanding, it grows stronger over time. Eventually, it could become so powerful that it tears apart galaxies, stars, planets, and even atoms themselves. Picture the fabric of space itself being stretched to its breaking point, ripping apart the very building blocks of reality. It's a terrifying possibility, but one that highlights the mysterious and unpredictable nature of dark energy. So what role does dark energy play in all of this? It's the driving force behind these scenarios. If dark energy remains constant or grows stronger, the big freeze or big rip becomes more likely. If it weakens, the big crunch could be on the table. The truth is, we're still unraveling the mysteries of dark energy, and its behavior will ultimately determine the universe's fate. As we ponder these possibilities, it's worth remembering that the universe's story is still being written. And with that, we're ready to explore another astonishing fact about the cosmos. Now, let's shift our gaze beyond the boundaries of our own universe and into the realm of the multiverse. What if our universe isn't the only one out there? The multiverse theory suggests that our cosmos might be just one of countless universes, each with its own unique set of physical laws and properties. This idea might sound like science fiction, but it's rooted in some of the most cutting-edge theories in physics, including quantum mechanics and string theory. One of the key pieces of evidence supporting the multiverse concept comes from the idea of cosmic inflation. During the universe's earliest moments, it's believed that space expanded exponentially in a fraction of a second. Some scientists propose that this rapid expansion didn't just happen once. It could have occurred in multiple regions, creating bubbles of space that each became their own separate universe. Imagine a cosmic foam with each bubble representing a universe, and our universe being just one bubble among countless others. Another fascinating angle comes from quantum mechanics, which suggests that every possible outcome of a quantum event actually happens, but in different universes. For example, if you flip a coin, in one universe it lands on heads, and in another it lands on tails. This idea, known as the many worlds interpretation, implies that there are infinite parallel universes where every possible version of reality exists. The implications of the multiverse theory are staggering. If true, it means that somewhere out there could be universes with entirely different laws of physics, where stars, planets, and even life might look nothing like what we know. It also raises profound questions about our place in the cosmos. Are we just one of an infinite number of possibilities? And if so, what does that mean for the uniqueness of our existence? While the multiverse theory is still speculative, it's a powerful idea that challenges our understanding of reality and pushes the boundaries of cosmology. As we continue to explore the mysteries of the universe, the multiverse remains one of the most tantalizing possibilities, and one that could forever change how we see the cosmos. With that in mind, let's dive into another mind-bending fact about the universe's expansion and what it means for the future of everything we know. Now, let's turn our attention to a cosmic puzzle that has left scientists scratching their heads: the Hubble constant controversy. The Hubble constant is a crucial number in cosmology because it tells us how fast the universe is expanding. Think of it as the speedometer of the cosmos. But here's the twist: depending on how you measure it, you might get different answers, and this discrepancy has sparked one of the biggest debates in modern astronomy. To understand why this is such a big deal, let's break it down. One way scientists measure the Hubble constant is by looking at the cosmic microwave background, or CMB, which is the afterglow of the Big Bang. This method gives us a snapshot of the early universe and suggests a specific rate of expansion. But there's another way to measure it by observing distant objects like supernova and Cepheid variable stars in the nearby universe. These objects act as cosmic mile markers, helping us calculate how fast space is stretching. The problem: these two methods don't agree. The CMB method suggests a slower expansion rate, while the supernova method points to a faster one. So, why the mismatch? Some scientists think it might be due to unknown physics, like a new type of dark energy or even a flaw in our understanding of gravity. Others suggest it could be a measurement error or a quirk in the way we interpret the data. Whatever the reason, this disagreement has become a hot topic in cosmology, with researchers racing to find answers. It's like trying to solve a cosmic mystery where the clues don't quite add up. The implications of this debate are huge. If the Hubble constant is higher than we thought, it could mean the universe is expanding faster than expected, which might change our understanding of its age and ultimate fate. On the other hand, if it's lower, it could hint at new forces or particles influencing the cosmos. Either way, resolving this controversy could lead to groundbreaking discoveries that reshape our view of the universe. As we continue to explore this cosmic conundrum, one thing is clear. The Hubble constant controversy reminds us that even the most fundamental aspects of the universe are still up for debate. And that's what makes cosmology so exciting. It's a field where every question leads to more questions, and every answer opens the door to new mysteries. With that in mind, let's move on to another fascinating aspect of the universe's expansion and what it reveals about the forces shaping our cosmos. Now, let's shift our focus to one of the most mysterious and elusive components of the universe, dark matter. While we can't see it directly, dark matter plays a crucial role in shaping the cosmos as we know it. Imagine the universe as a giant cosmic web, with galaxies strung together like beads on an invisible thread. That thread, it's dark matter holding everything together. So, what exactly is dark matter? We don't know its exact nature, but we do know it doesn't emit, absorb, or reflect light, which makes it invisible to our telescopes. Yet, its presence is undeniable because of its gravitational effects. For example, galaxies spin much faster than they should based on the visible matter alone. Without dark matter, galaxies would simply fly apart. It's like the glue that keeps the cosmic structure intact, ensuring galaxies and galaxy clusters stay bound together. But how do we know dark matter exists if we can't see it? Scientists detect it indirectly by observing how it influences the motion of stars and galaxies. One of the most famous pieces of evidence comes from something called gravitational lensing. When light from a distant galaxy passes near a massive object like a galaxy cluster, the gravity of the cluster bends the light, creating a magnified or distorted image. The amount of bending is often greater than what the visible matter can account for, pointing to the presence of dark matter. Dark matter also plays a key role in the large-scale structure of the universe. After the Big Bang, tiny fluctuations in the density of matter, both dark and visible, began to grow under the influence of gravity. Dark matter, being more abundant, acted as the scaffolding for these structures, pulling gas and dust together to form galaxies and galaxy clusters. Without it, the universe as we know it simply wouldn't exist. Despite its importance, dark matter remains one of the biggest mysteries in science. What is it made of? Is it a particle or something entirely different? These are questions that physicists are still trying to answer. What we do know is that dark matter makes up about 27% of the universe, far outweighing the 5% that's ordinary matter. It's a reminder that most of the cosmos is still hidden from our view, waiting to be discovered. As we continue to explore the universe, dark matter stands as a testament to how much we still have to learn. It's a silent, invisible force that shapes everything around us, and unraveling its secrets could revolutionize our understanding of the cosmos. With that in mind, let's turn our attention to another fascinating piece of the cosmic puzzle: the formation of the universe's first stars. Now, let's journey back in time to the very first stars that ever lit up the cosmos. These ancient stars, known as population 3 stars, were unlike anything we see today. Born just a few 100 million years after the Big Bang, they were the pioneers of the universe, setting the stage for everything that came after. But what made them so special? For starters, they were made almost entirely of hydrogen and helium, the only elements that existed in the early universe. There were no heavier elements like carbon, oxygen, or iron back then. These stars were pure, massive, and incredibly bright, burning through their fuel at an astonishing rate. The formation of these first stars was a monumental event. Imagine a universe that was completely dark, filled only with clouds of gas. Gravity began to pull these clouds together, and as they collapsed, they heated up until nuclear fusion ignited, creating the first stars. These stars were giants, hundreds of times more massive than our Sun, and they lived fast and died young. Their short lives ended in spectacular supernova explosions, which scattered the heavier elements they had forged in their cores across the cosmos. This was the universe's first act of recycling, seeding the space around them with the building blocks for future stars, planets, and even life itself. But why are these stars so important? Without them, the universe would have remained a dull, lifeless place. The heavier elements they produced, like carbon, oxygen, and iron, became the raw materials for everything that followed. They formed the second generation of stars, known as population 2 stars, and eventually stars like our Sun, which are part of the population 1 group. Every atom in your body, every piece of metal, every breath of air you take, it all traces back to those first stars. They were the cosmic alchemists, transforming the simple elements of the early universe into the rich diversity we see today. The legacy of population 3 stars is still with us, even though they vanished billions of years ago. Their light traveled across the universe, and while we can't see them directly, their fingerprints are everywhere. Astronomers study the oldest stars and galaxies to piece together the story of these cosmic pioneers. They're like the universe's first storytellers, revealing how everything began. And as we continue to explore the cosmos, we're reminded that the universe has a history, one that started with the birth of those first brilliant stars. With that in mind, let's turn our attention to another remarkable aspect of the universe's expansion, how it's not just galaxies moving apart, but space itself stretching. Now, let's shift our focus to something even more mind-bending. The expansion of the universe isn't just about galaxies drifting apart. It's about space itself stretching. Picture this. Imagine the universe as a giant rubber sheet. If you place dots on that sheet to represent galaxies and then stretch the sheet, the dots move away from each other, not because they're moving on their own, but because the sheet itself is expanding. That's exactly what's happening in our universe. Space itself is stretching, carrying galaxies along with it. This idea can be a little tricky to wrap your head around because we're used to thinking of space as empty and unchanging. But in reality, space is dynamic. It's not just a backdrop for galaxies and stars, it's an active participant in the cosmic dance. When we say the universe is expanding, we're not talking about objects moving through space, we're talking about space itself growing larger. This means that over vast distances, the space between galaxies is stretching, causing them to move away from each other at incredible speeds. To make this even clearer, think about baking a loaf of raisin bread. As the dough rises in the oven, the raisins representing galaxies move farther apart, not because they're traveling through the dough, but because the dough itself is expanding. Similarly, in the universe, it's the fabric of space that's stretching, pushing galaxies apart. This stretching happens everywhere, in all directions, which is why there's no single center to the expansion. Every point in space is moving away from every other point. This concept has profound implications for our understanding of the cosmos. It means that the farther away a galaxy is from us, the faster it appears to be moving away because there's more space between us to stretch. This is why distant galaxies are receding from us at speeds that can exceed the speed of light, not because they're breaking any cosmic speed limits, but because the space between us is stretching so rapidly. So the next time you look up at the night sky, remember that the universe isn't just a static collection of stars and galaxies. It's a living, breathing entity with space itself stretching and growing, carrying everything within it on an incredible journey. And as we continue to explore this expanding cosmos, we're reminded that the universe is far more dynamic and mysterious than we could ever imagine. With that in mind, let's dive into another fascinating aspect of the universe's structure, its geometry, and why scientists believe it's flat. Now, let's take a closer look at the shape of the universe itself. You might be wondering, what does it even mean for the universe to be flat? Well, this isn't about the kind of flat you'd think of when looking at a piece of paper. Instead, it's about the geometry of space on a cosmic scale. Scientists have determined that the universe is flat based on precise measurements of the cosmic microwave background, or CMB, which is the afterglow of the Big Bang. These measurements show that the universe's geometry follows the rules of what we call Euclidean geometry, the same kind of geometry you learned in school, where parallel lines never meet and the angles of a triangle add up to 180 degrees. But why does this matter? The shape of the universe tells us a lot about its fate. If the universe were curved like the surface of a sphere, it would eventually collapse back in on itself in what's called a big crunch. On the other hand, if it were curved like a saddle, it would expand forever, growing colder and more spread out. But because the universe is flat, it suggests a very specific future, one where the expansion continues indefinitely, but at a rate that slows down over time, leading to what's known as the Big Freeze. In this scenario, the universe would keep expanding, but its energy would become so diluted that stars would burn out, galaxies would drift apart, and the cosmos would grow colder and darker. This flat geometry also has implications for the total amount of matter and energy in the universe. A flat universe requires a very specific balance between these two, known as the critical density. If there were too much matter, the universe would curve inward, too little, and it would curve outward. The fact that the universe is flat tells us that the amount of matter and energy is just right to maintain this delicate balance. So when we say the universe is flat, we're not just talking about its shape, we're talking about its destiny. It's a reminder that even the most fundamental properties of the cosmos, like its geometry, hold clues to its past, present, and future. And as we continue to study the CMB and other cosmic phenomena, we're uncovering more about the universe's intricate design and the forces that shape it. With this understanding of the universe's flat geometry, let's turn our attention to another cosmic mystery, the Great Attractor, a gravitational anomaly that's pulling galaxies toward it in ways we're still trying to fully comprehend. Now, shifting our gaze to another cosmic enigma, we encounter the Great Attractor, a mysterious gravitational anomaly that's been pulling galaxies, including our own Milky Way, toward it at incredible speeds. Located roughly 250 million light-years away in the direction of the constellations Centaurus and Hydra, this invisible force is one of the most puzzling phenomena in the universe. But what exactly is the Great Attractor, and why is it so hard to study? The Great Attractor is essentially a region of space with an immense gravitational pull, so strong that it's drawing entire galaxies toward it. Imagine a cosmic tug-of-war where galaxies are being pulled across vast distances, all converging toward this unseen point. But here's the catch: our view of the Great Attractor is partially blocked by the Milky Way's own galactic plane, which is filled with dust, gas, and stars. This dense region of our galaxy obscures our line of sight, making it incredibly challenging to observe and study the Great Attractor directly. Despite these obstacles, scientists have managed to piece together some clues using advanced technologies like X-ray and radio telescopes which can peer through the dust. What they've discovered is that the Great Attractor isn't just a single object, but rather a massive concentration of matter, including galaxy clusters and superclusters, all contributing to its gravitational pull. One of the largest structures in this region is the Norma cluster, a dense collection of galaxies that plays a significant role in the Great Attractor's gravitational influence. But the mystery doesn't end there. Beyond the Great Attractor lies an even larger structure known as the Shapley supercluster, which may be contributing to the gravitational pull we're experiencing. This suggests that the Great Attractor is just one piece of a much larger cosmic puzzle, hinting at the complex web of matter and gravity that shapes the universe on the grandest scales. So, while the Great Attractor remains shrouded in mystery, it serves as a reminder of how much we still have to learn about the forces that govern our universe. As we continue to develop new tools and techniques to study these hidden regions, we're slowly unraveling the secrets of this gravitational giant and its role in the cosmic dance of galaxies. And with that, let's move on to explore another astonishing feature of the universe, its largest structures, which stretch the boundaries of our imagination. Now, let's zoom out even further and take a look at some of the universe's largest structures, colossal formations that stretch the limits of our imagination and challenge everything we thought we knew about the cosmos. One of the most jaw-dropping examples is the Hercules Corona Borealis Great Wall, a mind-bogglingly vast superstructure that spans an astonishing 10 billion light-years across. To put that into perspective, that's about 1/10 the diameter of the entire observable universe. This immense wall of galaxies, galaxy clusters, and dark matter is so enormous that it defies our current understanding of how such structures could form. The Hercules Corona Borealis Great Wall was discovered in 2013 by astronomers studying gamma-ray bursts, which are incredibly bright flashes of light that occur when massive stars collapse or neutron stars collide. These bursts act like cosmic beacons, allowing scientists to map the distribution of matter across the universe. What they found was a concentration of gamma-ray bursts so vast and dense that it revealed the existence of this enormous structure. But here's the problem. According to the cosmological principle, the universe should be relatively uniform on large scales. The discovery of such a massive structure challenges this idea, suggesting that there might be more to the universe's structure than we currently understand. Another fascinating aspect of these cosmic giants is how they form. The universe's largest structures are thought to have grown from tiny fluctuations in density in the early universe, amplified by gravity over billions of years. These fluctuations, which we can still see imprinted in the cosmic microwave background, eventually led to the formation of galaxies, galaxy clusters, and superclusters. But the sheer size of structures like the Hercules Corona Borealis Great Wall raises questions about whether our models of cosmic evolution are complete. Could there be other forces or processes at play that we haven't yet discovered? What's even more intriguing is that these structures aren't just random collections of matter, they're interconnected in a vast cosmic web. Galaxies and clusters are linked by filaments of dark matter and gas, forming a network that spans the entire universe. This web-like structure is a testament to the intricate dance of gravity and the distribution of matter on the grandest scales. And while we've made incredible strides in mapping this cosmic web, there's still so much we don't know about how it formed and how it continues to evolve. As we ponder these colossal structures, it's impossible not to feel a sense of awe at the sheer scale of the universe. The Hercules Corona Borealis Great Wall and other cosmic giants remind us that, even with all our advancements in astronomy, the universe still holds countless mysteries waiting to be unraveled. And with that, let's turn our attention to another pivotal moment in the universe's history, the inflationary epoch, a period of rapid expansion that shaped the cosmos as we know it. Now, let's rewind the cosmic clock to a moment so brief it's almost impossible to comprehend, just fractions of a second after the Big Bang. This is when the universe underwent one of its most dramatic transformations, a period known as the inflationary epoch. Imagine the universe expanding faster than the speed of light, doubling in size not once but countless times in the blink of an eye. This wasn't just any expansion, it was an exponential explosion of space itself, setting the stage for everything we see today. So, why does this matter? Well, the inflationary epoch solves some of the biggest puzzles in cosmology. For starters, it explains why the universe looks so uniform on large scales. If you look at the cosmic microwave background, the afterglow of the Big Bang, you'll notice it's remarkably smooth, with only tiny variations in temperature. Without inflation, this uniformity would be hard to explain. But during this rapid expansion, any irregularities were stretched out, leaving behind a nearly uniform cosmos. Another mystery inflation helps solve is the flatness problem. Measurements of the universe's geometry show that it's incredibly flat, meaning parallel lines stay parallel no matter how far they travel. Without inflation, this flatness would require an almost impossible level of fine-tuning in the early universe. But inflation naturally flattens the cosmos, much like how blowing up a balloon smooths out its surface. Perhaps most intriguingly, inflation also provides an explanation for the seeds of cosmic structure, those tiny fluctuations in density we see in the cosmic microwave background. They're thought to have originated as quantum fluctuations during inflation. Over billions of years, these fluctuations grew under the influence of gravity, eventually giving rise to galaxies, galaxy clusters, and the vast cosmic web we observe today. But here's the kicker. Inflation isn't just a neat idea. It's supported by a wealth of observational evidence. From the detailed measurements of the cosmic microwave background to the distribution of galaxies across the universe, the predictions of inflation align remarkably well with what we see. Yet, despite its success, inflation remains a theoretical framework, and scientists are still working to understand the exact mechanisms that drove it. As we reflect on this extraordinary period in the universe's history, it's clear that the inflationary epoch wasn't just a fleeting moment. It was a cosmic turning point that shaped the very fabric of reality. And with that, let's turn our attention to another mystery lurking in the cosmos, the missing baryons, a puzzle that reminds us just how much we still have to uncover about the universe. Now, let's shift our focus to a cosmic mystery that's been puzzling scientists for decades: the case of the missing baryons. Baryonic matter, the stuff that makes up everything we can see, stars, planets, gas, and even you and me, should, in theory, account for a significant portion of the universe's mass. But here's the twist. When astronomers tally up all the visible matter, they find only about half of what they expect based on the universe's early conditions. So, where did the rest go? The answer lies in the vast, invisible web of gas that stretches between galaxies. Scientists believe that a large portion of these missing baryons is hiding in the form of warm, hot intergalactic medium, or WIM for short. This elusive material is made up of extremely hot, diffuse gas that's so faint it's nearly impossible to detect with traditional telescopes. It's like trying to spot a single candle flame from miles away in broad daylight, challenging but not impossible. To uncover this hidden matter, astronomers have turned to some ingenious methods. One approach involves studying the light from distant quasars, incredibly bright objects powered by supermassive black holes. As this light travels through the universe, it passes through the WIM, which absorbs certain wavelengths. By analyzing these absorption lines, scientists can map out the distribution of this invisible gas, piecing together where the missing baryons might be lurking. Another clue comes from the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this ancient light provide a snapshot of the universe's early composition, revealing how much baryonic matter should exist today. When combined with observations of galaxy clusters and their gravitational effects, these measurements help narrow down the search for the missing matter. But the mystery doesn't end there. Some of the missing baryons might also be hiding in the form of faint, low-mass galaxies, or even within the vast voids of space, where matter is so sparse it's almost undetectable. The hunt for these elusive particles is ongoing, with new telescopes and technologies offering hope for a breakthrough. So, why does this matter? Understanding where the missing baryons are hiding isn't just about solving a cosmic puzzle, it's about piecing together the full story of how the universe evolved. These baryons are the building blocks of galaxies, stars, and planets, and their distribution holds clues to the universe's structure and history. As we continue to explore this mystery, we're reminded that even in the vastness of space, there's still so much left to discover. And with that, let's turn our attention to another fascinating chapter in the universe's story, the eventual end of star formation, a process that will shape the cosmos in ways we're only beginning to understand. Now let's journey into a future so distant it's almost unimaginable, a time when the universe itself will begin to dim. One of the most profound predictions in cosmology is that star formation will eventually come to an end. This isn't just a dramatic idea, it's a scientific inevitability tied to the very fabric of the cosmos. As the universe continues to expand, galaxies are slowly running out of the raw materials needed to create new stars. Stars are born from vast clouds of gas and dust, but over billions of years, these clouds are being consumed. Galaxies are like cosmic factories, turning gas into stars, but even factories run out of supplies. And once the gas is gone, the lights will begin to go out. So, when will this happen? Current estimates suggest that star formation will peak in about 1 to 2 billion years, after which it will gradually decline. By the time the universe is around 100 billion years old, the majority of galaxies will have exhausted their gas reserves. The last stars to form will likely be small, dim red dwarfs, which burn their fuel slowly and can shine for trillions of years. But even they won't last forever. The implications of this are staggering. Without new stars, the universe will grow darker and colder over time. Galaxies will fade, and the night sky, once filled with countless points of light, will become increasingly empty. This phase, often called the stelliferous era, will give way to a much quieter, darker universe. But what does this mean for life? If civilizations exist in the distant future, they'll face a universe where energy is scarce and the stars they once relied on are gone. It's a sobering thought, but it also highlights the incredible rarity and preciousness of the time we live in, a time when the universe is still vibrant and full of light. As we ponder this distant future, it's worth remembering that the universe is always changing. The end of star formation is just one chapter in its long, unfolding story. And with that, let's turn our gaze to another fascinating aspect of the cosmos: how the universe's accelerating expansion is reshaping not just space, but time itself. Now, let's shift our focus to a mind-bending connection between the universe's expansion and something we often take for granted: time itself. The accelerating expansion of the universe doesn't just stretch space, it also has profound effects on how time unfolds and how we perceive the cosmos. As the universe expands faster and faster, driven by dark energy, the distances between galaxies grow larger. This means that light from distant galaxies has to travel farther to reach us. Over time, this expansion will make it increasingly difficult for light from these galaxies to ever reach Earth. In fact, there will come a point in the distant future when galaxies beyond our local group will be so far away that their light will never catch up to us. They'll effectively disappear from our view, leaving us in a much smaller, isolated pocket of the universe. But here's where it gets even more fascinating. The universe's accelerating expansion doesn't just affect what we can see, it also influences the passage of time. According to Einstein's theory of relativity, time is deeply intertwined with space. As space stretches, time itself can appear to slow down from the perspective of distant observers. This means that for civilizations in far-off galaxies, time might seem to flow differently compared to ours. Imagine looking out into the cosmos billions of years from now. The universe will be a very different place. The stars and galaxies we see today will have faded into the distance, and the night sky will grow emptier as the expansion pushes everything farther apart. The universe will become a quieter, lonelier place with fewer clues about its vast history. This connection between expansion and time reminds us that the universe is not just a static backdrop, it's a dynamic, ever-changing entity. And as we continue to explore its mysteries, we're constantly reminded of how interconnected everything is, from the smallest particles to the largest structures in the cosmos. With this in mind, let's turn our attention to another intriguing piece of the cosmic puzzle: how tiny quantum fluctuations in the early universe set the stage for the vast structures we see today. Now, let's dive into one of the most fascinating aspects of the early universe: quantum fluctuations. These tiny, random variations in energy, smaller than an atom, played a monumental role in shaping the cosmos as we know it today. In the first moments after the Big Bang, the universe was a seething, chaotic soup of particles and energy. Within this chaos, quantum fluctuations created minuscule differences in density. Some regions were slightly denser, while others were a bit less dense. These tiny irregularities might seem insignificant, but they were the seeds of everything we see in the universe today. Over billions of years, gravity took hold of these denser regions, pulling matter together and amplifying those initial differences. The slightly denser areas grew into vast clouds of gas, which eventually collapsed to form stars, galaxies, and even galaxy clusters. In a way, the galaxies we observe today are the grown-up versions of those tiny quantum ripples from the early universe. What's truly mind-blowing is that without these fluctuations, the universe would have been perfectly uniform, a featureless expanse with no stars, no galaxies, and no structures at all. It's almost poetic to think that the grand cosmic tapestry we see today, with its swirling galaxies and glittering stars, owes its existence to these microscopic quantum quirks. This connection between the quantum world and the large-scale structure of the universe is a perfect example of how the smallest things can have the biggest impacts. It also highlights the incredible precision of the laws of physics, which allowed these tiny fluctuations to grow into the breathtaking complexity of the cosmos. As we marvel at the vastness of the universe, it's humbling to realize that its origins lie in something so small and fleeting. And with that thought, let's explore another piece of the cosmic puzzle: how the universe's temperature has been dropping since the Big Bang, shaping the conditions for life as we know it. Now, let's turn our attention to something that might sound counterintuitive at first: the universe's temperature. You might think of space as cold, and you'd be right, but it hasn't always been that way. In fact, the universe has been cooling down ever since the Big Bang. Back then, the cosmos was unimaginably hot, a blazing inferno of energy and particles. But as the universe expanded, it began to cool, much like how steam loses heat as it spreads out into the air. This cooling process has been happening for billions of years, and it's still ongoing. Today, the universe's temperature is just a few degrees above absolute zero, the coldest possible temperature where all molecular motion stops. This near-freezing state is most evident in the cosmic microwave background, or CMB, which is essentially the afterglow of the Big Bang. The CMB is a faint radiation that fills the entire universe, and it's a snapshot of what the cosmos looked like when it was just 380,000 years old. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. What's fascinating is that the CMB isn't just a relic of the past, it's also a thermometer for the universe. By measuring its temperature, scientists have confirmed that the universe has been steadily cooling over time. The CMB currently sits at about 2.7 degrees above absolute zero, a far cry from the trillions of degrees that characterized the early universe. This cooling trend has profound implications for the future of the cosmos. As the universe continues to expand and cool, the conditions for star formation will become less favorable, and eventually the lights of the universe may dim. But for now, this gradual cooling is a reminder of how dynamic and ever-changing the universe truly is. With this in mind, let's shift our focus to another astonishing possibility. What happens if the universe's expansion becomes so extreme that it tears apart galaxies, stars, and even atoms? Now, let's venture into a truly mind-bending scenario, one that could redefine our understanding of the universe's ultimate fate. Imagine a future so distant that the very fabric of reality begins to unravel. This is the possibility that dark energy, the mysterious force driving the universe's accelerated expansion, could one day grow so powerful that it tears apart everything we know. Here's how it could happen. As the universe continues to expand, dark energy's influence becomes more dominant. Over billions of years, this force could grow strong enough to overcome the gravitational bonds that hold galaxies together. First, galaxies themselves would be pulled apart, their stars drifting away from one another like leaves scattered by a cosmic wind, but it doesn't stop there. Over even longer timescales, the same force could rip apart stars, planets, and eventually even atoms themselves. This scenario, known as the Big Rip, is one of the most dramatic theories about the universe's end. It hinges on the idea that dark energy isn't just a constant force but one that intensifies over time. If this is true, the universe's expansion wouldn't just slow down or stabilize, it would accelerate to the point where nothing could hold together. What's fascinating is that this isn't just science fiction. Scientists have calculated that if dark energy behaves in a certain way, the Big Rip could occur in about 22 billion years. That might sound like an unimaginably long time, but in the grand timeline of the cosmos, it's a blink of an eye. Of course, this is just one of several theories about the universe's fate. Others, like the Big Freeze or the Big Crunch, paint very different pictures, but the Big Rip stands out because of its sheer scale and the profound implications it has for the nature of reality. It forces us to confront the idea that even the most fundamental structures of the universe, galaxies, stars, and atoms, are not permanent. As we wrap up this exploration, it's worth reflecting on how these ideas challenge our understanding of existence. The universe's expansion isn't just a distant phenomenon, it's a force that shapes everything from the largest galaxies to the tiniest particles. And while the Big Rip remains a theoretical possibility, it reminds us that the cosmos is full of mysteries waiting to be uncovered. With that, let's move on to our next topic, where we'll dive into the role of neutrinos in the early universe and how these elusive particles shaped the cosmos as we know it. Now, let's shift our focus to one of the most elusive yet fascinating players in the cosmic drama, neutrinos. These nearly massless particles are often called the ghosts of the universe because they interact so weakly with matter that they can pass through entire planets without leaving a trace. Yet, despite their ghostly nature, neutrinos played a crucial role in shaping the early universe and continue to influence its evolution today. In the moments after the Big Bang, the universe was a seething cauldron of energy and particles. Among these were neutrinos, which were produced in enormous quantities. As the universe expanded and cooled, these particles began to travel freely, carrying energy and influencing the formation of the first structures in the cosmos. Their presence affected how matter clumped together, ultimately shaping the distribution of galaxies and galaxy clusters we observe today. What makes neutrinos so intriguing is their ability to change forms or flavors as they travel. This phenomenon, known as neutrino oscillation, was a groundbreaking discovery that revealed neutrinos have a tiny amount of mass. Before this, scientists thought they were completely massless. This discovery not only deepened our understanding of particle physics, but also provided critical insights into the early universe's conditions. Detecting neutrinos is no small feat. Because they rarely interact with other matter, scientists have had to build incredibly sensitive detectors, often buried deep underground to shield them from other particles. One of the most famous neutrino detectors is the Super Kamiok, and in Japan, a massive tank filled with ultra-pure water surrounded by sensors. When a neutrino interacts with the water, it produces a faint flash of light which the sensors can detect. These observations have allowed us to study neutrinos from the Sun, supernova, and even distant cosmic events. The study of neutrinos has also shed light on some of the universe's most profound mysteries. For instance, they played a key role in the asymmetry between matter and antimatter in the early universe. Without neutrinos, the cosmos as we know it might not exist. As we continue to explore these ghostly particles, they remind us that even the smallest and most elusive components of the universe can have a profound impact. Neutrinos are a testament to the interconnectedness of all things, from the tiniest particles to the vastness of space. With that, let's turn our attention to another cosmic mystery, the Boötes Void, a vast region of space that seems almost empty, and what it tells us about the universe's structure. Now, let's journey into one of the most puzzling regions of the cosmos, the Boötes void. Imagine a vast expanse of space so empty that it feels like a cosmic desert, stretching across hundreds of millions of light years. This is the Boötes void, a region so sparsely populated with galaxies that it challenges our understanding of the universe's structure. Discovered in the 1980s, the Boötes void is one of the largest known voids in the observable universe. To put its size into perspective, if the Milky Way were placed at one edge of the void, it would take light traveling at its incredible speed around 330 million years to reach the other side. Yet, despite its enormous size, this void contains only a handful of galaxies, making it one of the emptiest places we've ever observed. So, how did such a massive void form? Scientists believe it's a result of the universe's large-scale structure, which resembles a cosmic web. This web is made up of dense filaments of galaxies separated by vast, empty regions like the Boötes void. These voids are thought to have formed as matter clumped together under gravity, leaving behind these enormous gaps. In a way, the Boötes void is like a bubble in the foam of the universe, a natural consequence of how matter distributes itself over immense scales. But the Boötes void isn't just a curiosity, it's a window into the universe's evolution. By studying voids like this, scientists can learn more about dark energy, the mysterious force driving the universe's accelerated expansion. Voids expand faster than regions filled with galaxies, and their growth provides clues about how dark energy behaves on the largest scales. Interestingly, the few galaxies that do exist within the Boötes void are often isolated and unique. Some of them show signs of unusual star formation, possibly because they've evolved in such an empty environment, free from the gravitational tug of neighboring galaxies. These galaxies are like cosmic loners, offering a glimpse into how the universe's structure influences the evolution of its inhabitants. The Boötes void reminds us that the universe is full of surprises. Even in its emptiness, it holds secrets that deepen our understanding of the cosmos. From the distribution of galaxies to the behavior of dark energy, this vast void is a testament to the complexity and beauty of the universe's design. With that, let's turn our attention to another fascinating chapter in the universe's story, the era of reionization, when the first stars and galaxies lit up the cosmos, bringing an end to the cosmic dark ages. Now, let's step back in time to one of the most transformative periods in the universe's history, the era of reionization. This was the moment when the cosmos woke up from its long, dark slumber and began to shine with the light of its first stars and galaxies. After the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen, creating a foggy, opaque environment. For hundreds of millions of years, the universe was plunged into what we call the cosmic dark ages, a time when no stars or galaxies existed to light up the void. But then, something extraordinary happened. Around 300 million years after the Big Bang, the first stars began to form. These weren't like the stars we see today. They were massive, blazing giants, hundreds of times more luminous than our sun. Their intense ultraviolet radiation began to ionize the surrounding hydrogen, stripping electrons from atoms and turning the foggy universe into a transparent one. This process, known as reionization, marked the end of the cosmic dark ages and the dawn of the universe as we know it. The first galaxies also played a crucial role in this transformation. As these early galaxies formed, their stars and supermassive black holes emitted powerful radiation, further ionizing the hydrogen around them. Over time, this process spread across the universe, clearing the fog and allowing light to travel freely through space. But how do we know all this? Scientists study the cosmic microwave background, the afterglow of the Big Bang, to piece together the story of reionization. They also observe some of the most distant galaxies, whose light has traveled billions of years to reach us. These observations reveal how the universe transitioned from darkness to light, giving us a glimpse into its earliest chapters. The era of reionization wasn't just a turning point for the universe, it was the foundation for everything that followed. Without it, galaxies like our Milky Way might never have formed, and the cosmos would have remained a dark, empty expanse. As we reflect on this pivotal moment, let's move forward to another astonishing aspect of the universe's story: the role of quantum fluctuations in shaping the cosmos as we know it today. As we wrap up this journey through the cosmos, let's take a moment to reflect on the incredible discoveries we've explored. From the universe's accelerating expansion driven by dark energy to the mind-bending concept of a multiverse, each fact has revealed just how vast, mysterious, and awe-inspiring our universe truly is. We've traveled back in time to witness the birth of the first stars, unraveled the secrets of the cosmic microwave background, and peered into the future to ponder the universe's ultimate fate. These 25 astounding facts remind us that the cosmos is far more complex and fascinating than we could ever imagine. But the story of the universe is far from over. Every discovery raises new questions, and every answer leads us deeper into the unknown. What lies beyond the cosmic horizon? Could there be other universes out there, each with its own set of physical laws? And what role will humanity play in unraveling these cosmic mysteries? As you ponder these questions, we'd love to hear your thoughts. Which fact about the expanding universe blew your mind the most? Share your favorite in the comments below, and let's keep the conversation going. If you enjoyed this journey through the cosmos, don't forget to hit the like button, subscribe for more mind-expanding content, and ring that notification bell so you never miss out on our next cosmic adventure. Until then, keep looking up. The universe has so much more to reveal.